So after we calculate a tangent line for a function, whatever slope that we got for the tangent line, we can associate that number and with the function we started with. And we can call that slope of that tangent line the slope of the function as well, even if that function we started with is not a line. So it's a little sleight of hand, but this is actually stuff that we can calculate. All we need to do is set up that slope formula, f of x minus f of a, all divided by quantity x minus a. And if that limit exists as x approaches a, we'll have a slope. Now, this slide is saying if we zoom in far enough towards the point, the curve almost looks like a straight line. This is exactly the picture that I was showing on my previous video with the magnifying lens. So I find that to be a very helpful picture to keep in mind. So here is a demonstration. This is exactly the parabola from the previous example. Here's the coordinate x equals 1, y equals 1. And as we zoom in, it does look more like a straight line. So we can say that that curve, that graph of the function y equals x squared, at the microscopic level, we may as well replace it with the tangent line that we know how to calculate now using limits. Now, we're going to be making this calculation a lot in this class. This is a very important idea for calculus, and this is the reason why we build up the theory of limits for, a good 3 or 4 weeks of this class. So let's simplify the formula a little bit and introduce a variable h. The idea is that h is going to represent my change in the x coordinate. So the slope of the secant lines, right, the blue lines where I've picked 2 different coordinates on the graph, and I just calculate the line in between them, that slope formula, rise over run, will always look like f of a plus h minus f of a, all divided by h. So that will be the same formula every single time for the slope of the secant line. So this formula actually gets a special name for as often as we're going to use it. The name is the difference quotient. So difference because we're measuring difference in the y variables. We're dividing by the difference in the x variables. Quotient's just a fancy word for division. And here is that very same picture drawn in again, now using the h instead. So it's helpful to remember that the coordinate a is something that we pick, and it is not going to change. We're trying to find the slope exactly at this point. X coordinate a, y coordinate f of a. Depending on the value of h, the slope that we calculate with the difference quotient may be more or less accurate. And the idea is that we get the correct value as we take the limit for h approaching 0. So this gives us a slightly different formula to find that slope of the tangent line based at x coordinate a. And the formula is in this box right here. The slope m is equal to the limit as the variable h approaches 0, and we are taking the limit of f of a plus h minus f of a all divided by h.